So now let's talk about this concept of enlarging the obstacles. Mathematically, this is represented using this concept of Minkowski sum. So this is defined for two sets. In general, if you have two sets, Minkowski sum is defined as a set that contains all the elements, where you can obtain by taking an element from one set and another from the other and adding them all. So for all pairs P and R, where P is from P and R is from R, you add them up, and the resulting set is the Minkowski sum of these two sets. Okay, so this might sound a little bit confusing. Let me just give an explanation here. So imagine that P is, let's say, a circle and R is a square. We think of these as a set of points. So circle is represented as a set that contains all the points inside the circle. Okay, so it's like infinite points inside. Similarly for a square over here. Okay? And in this case, the summation that we're doing is summation of vectors. So imagine that I have this coordinate system here. You take every vector represented by taking any point inside the circle, like this. And you take another vector by taking any point inside the square. Then you add them up, and let's say the resulting vector is that one, and that belongs to the Minkowski sum of the circle and the square. You do this for every pair of points, one from the circle and one from the square, and the resulting set will be the Minkowski sum of the circle and the square. Okay. We'll shortly see why this represents this concept of enlarging the obstacle. But now let's take a look at an example here. So you have, let's say, this polygon P, and you want to do a Minkowski sum with another polygon R. So the picture will look something like this. This is not 100% correct. I'm going to explain it later on, but this is just gives you one visualization of how this looks like. Okay. Before going into the obstacle, we're going to make some very interesting observation about the Minkowski sum of two objects. So assume I have this polygon P and a polygon R, and I want to do the Minkowski sum. And let's say Q is this Minkowski sum. The claim is that if you take any extreme point of Q, so for example that point is the result of adding one extreme point of the blue and one extreme point of the red. Okay? And in particular, it is the extreme point of this blue along this direction, and the same for red that needs to be added to get this one. Okay? So if you're not familiar, or if you don't recall the concept of an extreme point is essentially a point of a convex hull. And also an extreme point is defined with respect to a direction. So given a direction, let's say D, represented by a vector, the extreme point is obtained by the following operation. You take this object, you project it onto this direction, so let's project it down. The projection will create an interval, and you take the last point of the interval as you move along this direction. So the last point of the interval is this one, and it comes from the projection of that point. Okay. So why does this observation hold? Simply because of the way this extreme operation works. Because the extreme operation is essentially a maximum operation. You're looking at the maximum point along this direction. Okay. So therefore, if the maximum of two sets, the maximum of the sum of two sets is obtained by summing the maximum of one set to the maximum of another set. We can also prove it by contradiction. Assume that there is a point, assume that this point, let's say x, is not the result of the summation of two extreme points. So let's say there's another extreme point. So let's say x is equal a plus b, but there's another point a prime that is more extreme than a, okay, along this direction. Then you can easily see that a prime plus b will result in a more extreme point x prime, which contradicts the fact that assumption that x was the extreme point along that direction. So this is a very easy but also very fundamental observation that we're going to use later on. Okay. And in particular, one direct application of this is the following theorem. It says that if you do the Minkowski sum of two convex polygons with the n and m edges respectively, then the resulting shape is convex, and on top of it, it has n plus m edges. Okay? And in fact, we're going to prove something even stronger here, and that is the directions that you gain by doing the Minkowski sum is a union of the directions of the original polygons. In other words, every side of Q is parallel to one side of P or R. In other words, the side lengths of Q can be combined using the side lengths of P and R. Okay. How do we prove this? Well, it's not so difficult because we can just use this observation, right? Let's take the okay, first I'm gonna prove that this is convex. Okay. To prove that it's convex, we simply need to do a proof by contradiction, and that is, actually I'm gonna leave this for the exercise classes, so let's just assume that we have proven that this is convex, and then I want to show that it has at most this many edges and all the edges are parallel. Okay. Since we assume Q is convex, every it has take a convex take an edge of the polygon Q, let's say this edge E. All of the points along this edge are extreme with respect to the direction that is perpendicular to the edge. So take this direction D that is perpendicular to the edge, all of these points are extreme. Therefore, E can be written as the sum of some edge from P and some extreme points from P and some extreme points from R. Okay. If okay, and then the only way this can happen, because this is an edge, is that you're either summing up two edges, one edge from P, one edge from R, or an edge of one polygon and a vertex from another polygon, because the summation of a vertex plus vertex will just give you a vertex, right? So the only way you can get an edge as a summation from a Minkowski sum is that you sum a point with an edge. And also it follows that if you take an edge and you sum it with a point, you get an edge that has the same size, but it's also parallel. Because essentially Minkowski sum of a point, a single point, and any object is equivalent to translating that object with that vector v. So if you have a vector v and you sum it up with some object O, then you essentially get a translation of this object by the same vector v. Okay. So in that sense, when you sum up this edge and this point, you get an edge that is parallel and it has the exact same size. You essentially get a translation. And since this holds for all the edges of this convex Q, then we can say that Q has n plus m edges, and in fact all the side lengths of Q are equal to the side lengths of the polygons that we use. If the two edges of two polygons are parallel, so let's say you have this edge plus this edge, then the Minkowski sum of two edges that are equal will be an edge that is parallel, and its total length is the sum of the total length of the resulting sets. So as a consequence, in fact, we have proven that the perimeter of Q is equal to the perimeter of P plus perimeter of R.